Yesterday we talked about rewriting logarithms in exponential form and vice versa, right? And this is the key thing that I want you to be able to do from yesterday, is that if I give you a logarithm, you can write it as an exponent, and if I give you an exponent, you can write it as a logarithm. The other important thing from yesterday was this right here. These are our two, I'm going to put it in quotations, math lazy logarithms, where we don't necessarily write the base. So for these two, log base 10 of x is our common logarithm, and it's going to be the one where it's just written as log of x. There is no base. So if you don't see a base, it's a 10. Same thing for the log base e of x. That was another really common one. So if you just see ln of x, the natural log of x, the base is e. Okay? So today we're going to talk about simplifying using inverses. So really this should say using inverses. So I'm looking at example 4, where it says simplify the expression, and really that should say using inverses.
Hold on.
So simplify the expression using inverses. So every math operation on the planet has an inverse. An inverse is something that can undo the original operation. And I want you to remember logarithms are an operation. So addition, inverses, subtraction, multiplication, inverses, division, and so on. So that means that logarithms have an inverse as well, and that's raising something to an exponent. So part A, we have 10 log 4. What's the base on that log? Not written, but what is it? Yeah. It's a 10. So this is the same as 10 log base 10 of 4. What you're looking for here is that in order for these to be inverse operations that undo each other, the base of the exponent matches the base of the logarithm. If they match, I hate saying this expression, but they cancel out, they undo each other, and this is just gone. And what you're left with is just that 4. The 4 doesn't stay in the exponent, it's not just some floating thing. It comes down to your remaining 1. And that's actually it. Yeah. So let's look at part C. I'll come back to B in a second. So part C, we have e natural log of 9. Okay, so again, remember, the natural log is the same as log base e of 9, but we never write it that way. We always write it with that ln. And that is an ln, not a constant. So again, what you're looking for is that this base matches the log base. If they match, they undo each other, and you're just left with 9. Yeah.
You have like these problems on. So like 3 minutes short.
Yeah, you don't have to show your work on the homework for these ones. If it's like a one-step thing like this, yeah. I don't know what you would show. So if you look at part B, it's a little different because now, first of all, we're starting with a logarithm, and then those bases don't match. So it doesn't matter what order you start with. If part A had been instead written as log base 10 of 10 to the 4th, that's the same thing. It would still be 4. Those would still cancel out. Okay? So it doesn't matter if you have 10 raised to a log or if you have a log of an exponent. As long as the bases match, they still will undo each other. So part B, we want to make those match. So in part B, we have log base 5 of 25 to the x. How can I make that 25 look like a 5? I hear all the right ideas. So we have multiply by 5, divide by 5, square root, yeah. What we want to do is we want to write it as an exponent. So you have log base 5 of 25 is the same as 5 squared to the x. You can multiply in that x. So you have log base 5 of 5 to the 2x. This is is about as challenging as these problems get, because again, log base matches the exponent base, so those just undo each other, and what you're left with is just 2x.
How did you put that to the 5?
You put 5, that's multiplied by the 2.
Oh.
That's the exponent rules, just say that if you're raising a power to the power, we multiply the 2. And honestly, I put it on the outside just in case something is more complicated where you would have to multiply it to multiple pieces, but normally it would just be that it's 5 to the 2x, or whatever the power is. So part D, same thing, I have a log base 3 of 27 to the x. I want that 27 to look like a 3. So what power of 3 is 27? The third. So we have log base 3 of 3 to the 3 raised to the x. We multiply in that x. So we have log base 3 of 3 to the 3x. As soon as those match, they undo each other. You're just left with the 3x. Nice, right? Log of an exponent. Pretty cool. Does get a little bit harder. So that's using inverses to simplify these expressions. But since there are inverses out in this math world, I think we have to be able to find those as well. So example 4, example 5, wants us to actually find the inverse of the function. So if you remember from chapter 3, when we were finding the inverse of radical functions, that's where we switched our x and y, and then we used all those different roots to solve for y. We're going to do the same thing here. So part A, we have y equals 6 to the x. Your first step is that you're going to switch your x and y. So you'll have x equals 6 to the y. The second step, if you start with an exponent, your final answer is going to have a log in it. If you start with a log, your final answer will have an exponent. So your second step here is to solve for y using logs. So if I want that 6 base to go away, what base on my logarithm do I want? Yeah, I want the 6, because I want those to be the same. So what you're going to do, whatever you do to one side, you must do to the other side. So you're going to have log base 6 of x equals log base 6 of 6 to the y. Okay, a couple things to notice here. First of all, in terms of like placement where things are, this 6 is on a level with that log, right? Because we have a subscript, we have the normal level, and then we have a superscript now to worry about, and it matters where you put these. So the 6 is on, I'm putting quotations, the normal level, on the level with that log. The sub, I'll show you where that is on your keyboard for go formative, but that's down below, and then this y is in the exponent spot. But again, these will cancel out. When they cancel out, this y goes down to the normal level. So you're left with log base 6 of x equals y. And then just because we want it in standard form, it should go y equals log base 6 of x. On Go Formative, to write that base, there's 2 ways to do it. Go Formative has the button on their keyboard, it's next to their exponent button. Or if you have an actual keyboard, it's shift and then the button next to the 0, that's the minus, that's your subscript. So shift minus button will take you down, just like the shift 6 will take you off the back here. Any questions about number 1? Okay, so that's if you start with an exponent. Part B, we're starting with a log here. So we have y equals the natural log of x plus 3. Your first step is still to switch your x and y. So you'll have x equals the natural log of y plus 3. base on natural log. It's not written, but what is it? Okay. It's E. Yes, natural log is E. So that means that you're going to raise both sides to the E. Okay, second step, solve for y. This time you're going to use exponents. So we're going to have e to the x equals e to the natural log of y plus 3. So now I know that students who do not like this. The natural log is in your exponent. It's up top. So it's not e times the natural log. It is e raised to that natural log. So those will cancel out. And you'll be left with e to the x equals, this whole thing comes down. You can drop the parentheses. And you have y plus 3. You want the y by itself, so you subtract 3 from both sides, and then you can switch the order too, so y equals e to the x minus 3. So again, if you start with an exponent, your final answer will have a logarithm in it. If you start with a logarithm, your final answer will be an exponent. Okay? The only difference there is that you're going to go both ways. Any questions about that one? Alright, let's look at part C. So we're starting with an exponent, so my final answer is going to have a logarithm in it. It's y equals 4 to the x. My first step is to switch x and y. So I have x equals 4 to the y. Then I'm going to take a log on both sides. What is the base on my log going to be? 4. So I have log base 4 of x equals log base 4 of 4 to the y. These will undo each other. So we're just left with log base 4 of x equals y, and then, since I'm thinking about it, y equals log base 4 of x. Any questions about that? Feel okay about finding inverses so far? Okay, I want to make a slight alteration to part D, just because we do have to kind of talk about your order of operations here. So for part D, if you take your pencil and turn it to white, just white out this side of the parenthesis and put the parenthesis right here. So if you remember from chapter 3, I always told you before taking a root to get whatever was being raised to a power by itself before you do that. The same thing is true here, so don't write down this next part. What's the base on this logarithm that it's not written? Yeah. It's 10. So, and again, don't write down this part. I'm going to write down bad math here. If you raise 10 to both sides, you have 10 to the y equals 10 to the log of x minus 5. This minus 5 is a big issue. There is no reason to think that this just cancels out, and then like what happens to minus 5? It's just floating there. So that doesn't undo that. So that means that before you raise both sides to the 10, you need to move this minus 5. So again, we're switching x and y. So we have x equals, you can start writing log of y minus 5. Before I raise both sides to the 10, I need to add 5 to both sides. So we have x plus 5 equals the log of y. Now I'm going to raise both sides where 10 is the base. So I have 10 to the x plus 5 equals 10 to the log of y. So, again, a couple things here. This whole thing is your exponent, not just one part of it, the whole thing. Because whenever you do to one whole side, you do the other whole side. Then the other thing is we don't write the base here, but remember this is a base 10, so these do cancel out. And you're left with 10 the x plus 5 equals y. So we switch the order, y equals 10 to the x plus 5. There's a couple on your practice today that do that where the order really doesn't matter and where parentheses matter. So I just want to talk about one last thing before we set you loose. Some common misconceptions I see about logarithms. Some students treat logarithms like they're numbers. So I'll see something like log base 4 raised to the second. That makes no sense. That's like putting a plus raised to the second. Okay, it's an operator. It's not a quantity. You can't raise it to the second. The other thing is there is a difference between, say, log base 2 of x plus 1 and log base 2 of x plus 1. Those are two different things. Okay, again, log is an operator. It's essentially an operator on whatever that expression is. So if it's operating on x plus 1, that's different than operating on just x and then adding 1 to that comment. So be aware of those differences because sometimes you're going to need a parenthesis. Yeah.
Why do we use the parentheses on example B?
Because otherwise it looks just like example C. No, it looks like example B. And I wanted you to see the difference. Do you see how in this example B, we ended up with the exponent and then minus the number down below? Versus in example D, it's all in the exponent. I wanted you to see the difference. Okay, so you guys can start working on your practice. It's chapter 4.45